Hi, pre-calculus students. We are going to look at, not all, but we're going to look at two of the problems from class today. And I feel like you guys are pretty good with ellipses, so we're going to focus on hyperboles. Hyperboles, that's from your other class. Hyperbola, not to be confused with hyperbole, is what you're looking at right now. And this was the one from the front page of the pages that I gave you today. We're going to do this one and then the hyperbola on the very next page. So we need parametric equations. So we're going to have x and y, and one of these is going to be tangent and one is going to be secant. So the method I suggested was that you think of this as like a street. I'm making like street dashes like the middle of a road here. Kind of corny, but this is like a street. So that means that we have secant first and then tangent, because ST makes you think of street. Okay. And of course the argument is T. Now we need to know what is, we're going to have plus H, right? We've got an H here. And plus k. We got these unknowns, right? Now h and k, if they were 0, then the center of this hyperbola would actually be here at the origin. If h and k were 0, this would be the center of the hyperbola. Instead it's here, and that is at 0, 6. So that's my h and that's my k. It's really as simple as that. So I can easily get my h and k, come on now, is 0 and 6. And since that's 0 and I'm adding 0, I can just get rid of it. So I have secant t and I have tangent t plus 6. But I'm forgetting, of course, what goes in front of it. I need an a coefficient and I need a b coefficient. Once I have those, I'll be done. I'll have my parametric equations, or at least I'll be done with this part of it. So I can look to, now when it was an ellipse, we were looking at, like if this were an ellipse right here, I'd be interested in this dimension, the length of this axis, and in particular, I'd be looking at the distance from the center to the endpoint, basically half the length of that axis. Well, that radius type distance is important here too. So from the center to this, which we call a vertex, and there's another vertex over here, this distance is 2, right? You can see that easily. Now that's a horizontal distance, having to do with horizontal scaling. And so we can simply put that here. We know it's the coefficient associated with x. We know it's the coefficient within the x equation because it's a horizontal distance and represents a horizontal scaling. Okay, now as far as a vertical scaling, we don't have anything really easy to measure. We can't just, say do this and say, oh, well, that's our vertical distance, so we'll put it here. And it doesn't work that way. So, but the good news is we have everything except for this one unknown. So if we wanted to, we could pick a point and we could go ahead and sub it in there and basically hope for the best and basically say, all right, if we sub in that point, if it's close enough, then B will probably be close enough. Now, depending on what you're trying to do with this hyperbola, close enough is a relative thing. But right now I'm all about estimation and being reasonable. So we'll get a reasonable value for B, even if we don't get the exact value. Now let's see, what's the closest? In class I was suggesting that this one was pretty good. Well, now that I look at it, I feel like the curve misses it pretty cleanly. Same thing here, but at least we're a little bit closer. So maybe we'll go with this one. You see why I chose that? It's basically an integral point because this is where the lattice, grid lines meet at a lattice point. So this is where x equals 10 and where y equals 11. Okay, so think about what I'm doing. I have all my, everything's filled in basically, except for not everything's filled in, but basically what I have is two equations. This is the only thing that I need. That's what I should have said. This is the only thing that I don't know that I still need to know in order to complete my parametric equations. And so I can get that by using any point, including this one. This one will work just fine. I can take these coordinates, put them in for x and y, and see what it looks like. 10 equals 2 secant t, because 10 is an x value. And simultaneously then 11 would equal b times tangent t plus 6, right? So for some particular t, and this is the point, t for some value makes this equation true, and the same value for t would make this equation true when b is the proper value that we want. So we're basically now just solving the system of equations. So let's go ahead and do that. All right. Now to solve the system of equations, and again our goal is to get b, to solve the system of equations, this one we want to work on this one first. Why? Because this equation has only the one unknown now, t, right? This equation we don't know t, well we don't know the particular value for this parameter, and we don't know b. So here we have two unknowns, here we have one. So we're going to deal with this one. Okay, so let me do that over here off to the side. So we'll say 10 equals 2 secant t, and therefore if I divide both sides by 2, I have 5 equals secant of t. Okay, so far so good. Now remember that secant is 1 over the cosine of t here, right? Secant is the reciprocal of cosine. So if I get the reciprocal of 5, I will get cosine itself, right? Now you should recall how to solve this equation. If the cosine of t is 1/5, the inverse equation would be that the arc cosine, or inverse cosine of 1/5, equals t. So that's something you can plug into your calculator, and I'm just going to have to pause this so I can do that myself. So just hang on for a second. Okay, I'm back, and t, it turned out, was equal to 1.369. So this particular value for the parameter makes this equation true, and we are interested in what happens in this equation when t takes on that same particular value. So we're now going to deal with this equation, and we'll do that over here also. 11 equals b, don't get that mixed up with my 6, times, this is a b here, this is b, times the tangent of 1.369 plus 6. So I'm subtracting 6 from both sides, b, and I'm taking the tangent of this value, and I'd better run away and do that now, so hang on. Okay, so it turns out that here 5 equals b times, and this tangent is 4.888, and if we divide on both sides by 4.888, we get something like 1.022 equals the coefficient b. So this thing right here that we were looking for, we found it. This is now, and let me erase everything so I can, okay. So so this is now 11 equals 1.022 times the tangent of t plus 6. And now I can write properly my, my parametric equation. So I have x equals 2 secant t, and I have y equals 1.022 times the tangent of t plus 6. Okay, now here's something that we should point out. This number is really close to 1, right? And we got it by approximating, right? This curve does not go exactly through 10, 11. So we're approximating this coefficient because 10 and 11, that's an approximate pair, ordered pair for this relation. We don't even think it's really entirely accurate. So therefore, maybe 1 exactly is the number. So it's worth testing that out. So you can do that for yourself. However, 1.022 is good enough for right now. And when I say good enough, I mean that for if you make the window like about this big or even bigger than this, 1.022 and 1 will be very close. Now, if we're talking about values way down the line, right? If we're going to use this as some kind of a model and we're looking at, t-values that are extreme and take us way down the curve, yeah, this will eventually make a difference. So I'm not going to claim that this is, just as good in every situation. But for me, for us right now, it is just as good. I'm happy to see this based on your your convincing work that you show me, and so that'll be good enough. Now, if you don't go through all of this, if you want to just try a value and see, that's the only value we didn't know that wasn't that easy to get. So if you just try stuff out and you get it pretty darn close, then for right now I'm good with that too. So here we have our parametric equations. All right. Now I just want to look at how would we take. Can I do this? No, I can't do that. Boy. All right. Never mind. Okay. So how would we take this and make it rectangular? I want to go rectangular with this thing. I've got parametric. I want rectangular. It's going to depend on, well, no, I shouldn't say depend on, but it's going to be based on the Pythagorean identity, tangent squared plus 1 equals secant squared of the same argument. So we're going to take our x equation here and divide both sides by 2. So I'll divide this by 2, I get secant t, and I'll divide this by 2 and I'll get x over 2. Same thing here, I got to solve for tangent of t here. So I'm going to subtract 6 from both sides. I'll get y minus 6. I'm going to divide by 1.022. And I'm left with tangent t on the right side. Now I have secant, which I see here, and I have tangent, which I see here. So I'm going to go ahead and square both equations. Both sides of both equations. X squared over 4 equals secant squared. And then the binomial squared y minus 6 over whatever this is. We probably want to figure out what that is, but equals tangent squared. So now, since we have tangent squared t, which I see here, and we also have secant squared t, which I see here, right? We can sub this in for tangent squared, we can sub this in for secant squared, and we'll have our rectangular equation. So here we go with the rectangular. Okay, so instead of tangent squared, I'm writing y minus 6 squared over, and you have a calculator, I'm sure, you can figure this out. What is 1.022 squared? Plus 1, right? So it was tangent squared, which is here, plus 1, I bring that along, equals secant squared, which is equal to x squared over 4. Okay, and you can manipulate this and write it in different ways, but this is fine. That's a rectangular equation. All right. Okay, one more example. We'll go a little faster with this one. Let's see. Go a little faster this time because we know everything. We already said it. All right. There we go. And okay, so what's the story here? So I'm going to have x equals and y equals, my parametric equations. In this case, we said since we have like a hill here, which is kind of like a tower or a hill. Again, this is a ridiculous mnemonic device. It's corny, but it helps you guys remember because I hear you guys repeating it a lot already. But this is a tower, which means tower makes you think of T, and S, which means tangent comes first and then secant. So that means that for the x, get rid of that nonsense. We'll get, for the x equation, we need tangent of t. Of the y equation, we need secant of t. Okay, and then we need our h and k. So we have to look for our center, which is here, at 3, -4. That's my h, that's my k. In you go. Now we need our coefficients. First coefficient is the distance here, 3, right? This is a vertical distance. This is associated with a vertical scaling, and so it is the coefficient within the y equation. So all that was pretty simple. Now we just have to deal with this. So we try different things. Maybe we play with this in the calculator. We get pretty close and we put something down there and call it a day. If you're going to solve for it directly though, pick a point. Now here's the thing, when you pick a point, you can't pick the vertices. That won't work. And if you try it, you'll see why that doesn't work. And you also shouldn't pick a point that's too close to the vertices. Let's go a little farther out, because if we only base it on what's in here and we estimate it, then that means pretty quickly we're going to get off track. All right, so let's see. None of these are looking too attractive, though, I've got to say. I mean, I don't know. That one's kind of close to a half. I could just deal with that. Okay, well, yeah, it's all the same. We'll just say 12, 5.5. Okay, so it's not integral, but that's okay. Good enough. So we'll do, we'll plug those in. 12 equals a times tangent t plus 3. And 5.5 equals 3 secant t plus -4. So again, this equation has 2 unknowns. This has only 1. So I definitely want to solve this one. So I add 4 to both sides. And I divide by 3. And whatever that is, I'll take the... Okay, well, I'll go ahead. I don't have to simplify it. Now, since the secant of t equals that, I'll do a reciprocal, since cosine is the reciprocal of secant, it's going to be equal to the reciprocal of this fraction. And now I do arc cosine of that equals my t. And now just give me a second to get this value. Okay, so I went ahead and did that, and here's what I found. When we solved this, we got that t is very close to 1.25, right? We then take this value and we plug it into the other equation where we're going to end up solving for a. Okay, so let's go ahead and do that. We're going to have 12 equals a times tangent of 1.25 plus 3. Now, tangent of 1.25 is itself very close to 3. So I'm just going to, since I'm estimating anyway, I'm just going to write 3. Tangent of 1.25 is 3 times a is my 3a plus this 3 from the equation. So I go ahead and I solve. I subtract 3 from both sides. I divide by 3. A equals 3. Okay, so I fill that in. So I have x equals 3 tangent t plus 3 and y equals 3 secant t plus -4. Those are my parametric equations. And from there, I can do my rectangular by solving for tangent first. I subtract 3 from both sides. It's going to be x minus 3 right here. Then I divide by this 3. And I have this is equal to tangent of t. Then I do the same thing here with my y equation. I add 4 and divide by 3. So I have y plus 4 over 3 equals secant of t. I square them. I'm going to square my equations. And then once again, I'm using tangent squared plus 1 equals secant squared of the same argument. So I wind up with, by subbing in, I wind up with x minus 3 squared over 9, which is equal to tangent squared, which is right here in the equation. So this tangent squared is now this. I bring with me plus 1, and that is equal to secant squared, which is now written like that. There you go. Okay, so we have rectangular equation, rectangular equation for this hyperbola, and we have the parametric equations for this hyperbola. Okay.